Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to learn about the 5 basic transcendental functions that you're expected to know at this level of calculus. Your first question is probably, what's a transcendental function? Now that's simply the name we give the classification of functions that are not algebraic. And usually that involves the trigonometric, the exponential, and the logarithmic functions, among a few others. Now, in this level of calculus, these are the 5 that you're kind of expected to know and be able to break out kind of on a whim. There are others, including the other trigonometric functions like the inverse functions and some of the more complicated ones, but typically for those you're either going to have a table where you can look at what those kinds of derivatives will look like, or you'll be able to derive them when you need them. Usually, if you're in kind of a specialty field where you're going to need those kind of complicated situations, you'll either be working with them enough that you'll know them, or like I said, you'll have some kind of table where you can use those. Now, when it comes to your exponentials and your logarithms, obviously there's more than simply the natural log and Euler's number, but again, there are other techniques that we're going to be using with those, and E is one of the only exponentials where it's its own derivative, and the natural log just happens to be a very interesting situation where when you take the natural log of the absolute value of x, or the natural log of x when x is strictly in the positive numbers, then you're going to get 1 over x, and this is a very useful situation that we're going to be using in future videos. Now, in this video, this is going to be very proof heavy, so there are not going to be exercises at the end, and we are only going to be proving these 3 derivatives, because while we can prove the derivative of e and the derivative of the natural log, we can't prove it yet with the tools we have, because either we need to know a little bit more about a series, or we need to know the chain rule, or we need to know how to deal with indeterminate forms. All tools that we will have by the end of this course, or by the end of a calculus course, we just don't have them yet. So let's go ahead and look at proving the derivative of sine. So here we have the first part of our proof. It starts out exactly like you'd expect. We've got our definition, and we just put in our x plus h. Now, because we're taking the sine of a sum, we go ahead and use our angle sum theorem for sine, which tells us we've got the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. We gather up the like terms, so we've got the sine x minus the sine x here, cosine's there. That allows us to factor out the sine x. Now, the reason we want to do that is because when we distribute this limit through using our limit laws, this sine x is just going to be sine x because we're taking the limit as h approaches 0. Has no effect on sine x. Similarly, cosine x is cosine x. No big deal. So what we really care about is this situation 2 and situation 4. We can't really do anything here because we don't have the tools to directly evaluate this limit as it is. Okay, we will learn some tools later that we could do this with. Similarly here, we've got a problem down here with this, okay, for similar reasons. But if we look at this one, we can actually do something with this one that we can't do with this one, because we have a cosine h minus 1. And anytime you've got that, that should really ping off in your brain, Pythagorean theorem with trigonometry, right? So if I multiply by the conjugate, right, cosine h plus 1 over cosine h plus 1 in this situation, that's going to give me cosine squared minus 1, which will let me convert via trigonometric Pythagorean theorem into negative sine squared h. But the reason I do it isn't because I care about the top, it's because I needed to deal with that h in the bottom. I mean, yeah, this was a 0 in the top, but it's still going to be a 0 in the top. However, now in the bottom, I have that h is 0, but over here I've got this cosine of h plus 1. And if you follow it through, over here I get sine h, well that's the limit as h approaches 0 sine h, that's 0. And cosine of h, that would be 1 plus 1 ends up being 2. So that's 0 over 2. That's 0. And then this is negative sine h. would be 0 over, oh, h is approaching 0, 0. But if this exists, then I've got 0 times something. So this would become 0, which means I would have sine x times 0, so 0, meaning that goes away, and then the cosine x times this, so whatever this is, which means that's all I care about is this term. And considering that our expectation is that the derivative of this is cosine x, we're pretty sure that's going to be 1, but we need to prove it. Now, like I said, we do have some sophisticated tools we could use to prove this, but we haven't gotten those tools in this curriculum yet. But we do have some classic tools we can use to do this. We can use a geometric proof using the unit circle and things that we know from geometry and trigonometry. And that's what we're going to do. We're going to find out exactly what this is using geometry and our friend, the squeeze theorem. Watch. So it looks a little intimidating, but if you like geometry, it's really not that bad. We start with a pretty innocuous statement, which is that we're going to take the limit as h approaches 0 of sine h over h. Now, because we're going to work with the unit circle, we could work in any quadrant, and honestly, most of the time we end up just shifting everything to work in the first quadrant anyways. So our first statement here is just that we're going to limit ourselves to working in the first quadrant, which is that h is going to be between 0 and pi over 2. And also that kind of tells you that we're going to be working in radians. That does make the proof significantly easier because that means that we can work in arcs. Now, what we say here is that we're going to let B be any arbitrary point on the unit circle in quadrant 1, and then we're going to let C be a point on the x-axis, so the line x, such that BC is perpendicular to x. So we have B here and C here, and I've marked it with a right angle. So by the triangle inequality theorem, okay, we also have A marked here at the end, by the way. That's just where the circle intersects our x. By triangle inequality theorem, BC is less than BA, which is less than the measure of the arc AB. So what this is saying is we have a triangle that's here. We're looking at this triangle ABC, and AB is the hypotenuse of this little right triangle. And in a right triangle, the hypotenuse is the longest side. So therefore, BA has to be longer than BC by inequality theorem. And this arc is clearly outside that right triangle, so it's bigger. Okay? Now, that arc is exactly equal to the angle that subtends it. Okay? So that arc has the same size as the angle h. That's all that's saying, okay? Now, the other thing we know is that this angle, because it is in this triangle right here, OBC, we know that that would be sine. That's the definition of sine, right? But we know that OB, because this is the unit triangle, happens to be 1, which is what we're saying here. So this tells us that the sine of h is less than AB by here, okay, which happens to be less than h, which is this arc. So all we're saying is that the sine of h is less than h, and then we use a little bit of algebra to tell us that the sine of h divided by h is less than 1. That's going to be our first limit. That's our upper limit, okay? So now we need to get our lower limit. And for this one, we need to get a little bit clever. And so we're going to use the concept of tangents, and what we're going to do is we're going to circumscribe the circle with a polygon. And we're going to do this with tangent lines, creating a polygon. This is very similar to how Archimedes designed his proof by exhaustion of pi, where he found pi out to a truly ridiculous number of digits via calculation. Okay? So in order to do this, we construct a couple of tangent lines and a projection of the line OB. So we simply project OB out to some arbitrary distance, it doesn't matter. And then we construct the tangent at A and the tangent at B such that they are part of some polygon. It doesn't matter the size of the polygon, none of that matters. It only matters that we're tangent at B and we're tangent at A, and that we intersect at E, and that our tangent at A continues its projection up until it intersects the projection at O. Now, I didn't write all this out because we have our diagram and I can explain it, okay? So what this does is this creates this large triangle here, okay? Now, it's not written in a way that you can tell that this is a right triangle here, but because this is a tangent, if you remember any of your geometry, a tangent is always perpendicular to the point of tangency, and so because we're tangent at A, this is a 90-degree angle. I know it's not drawn that way, but that's because I'm not the greatest artist, okay? Similarly, that's how we know that this is a 90-degree angle, because this is the point of tangency. So this is 90 degrees to E, okay? That's going to be important because we're going to again use triangle inequality theorem for the next part of our proof, okay? Now, where we're at here is we are here, okay? So BE and EA are the sides of a circumscribed polygon tangent at B and A. That demonstrates the 90 degree, and because it is a circumscribed polygon, we know that BE plus EA is larger than that arc which happens to be the same size as H. So therefore, the measure of the arc is less than BE plus EA. However, because this triangle is here and it creates this right triangle because of this tangency, this is a hypotenuse of this little triangle. So we know that this hypotenuse here is the biggest side in this little triangle that BE is part of. So we know that this side, doesn't matter how big it is, we know it's bigger than this side. And that's all we care about because we're working with inequality, right? So therefore, we can replace the BE with this piece. But the reason that's an advantage to us is because it's part of this long line here that's part of this triangle here. All of this is done just with simple projections and geometric truth, okay? What that lets us say now is that that arc here is less than the length of this side, okay? So the length of the arc BA is less than DA. Definitively, we know that is true. The length of the arc is still equal to H. That hasn't changed. But DA, via trigonometry, right, is now we're going to take the tangent. So H tangent is the opposite over the adjacent, so it's going to be DA over OA, but we don't want that, okay, because we have DA. So that means it's OA times the tangent, but OA happens to be the radius of the unit circle, so we know that OA is 1 because this is the unit circle. So OA is also 1, so that means that DA is equal to the tangent of H. So thus we know that H is less than the tangent of H, but the tangent of H is also defined as the sine of H divided by the cosine of H. So a little bit of algebra, we multiply the cosine over, divide the sine over, and that gives us that the cosine of H is less than the sine of H divided by H. So now we have the sine of H divided by H is greater than the cosine of H, but is less than 1. And if we take the limit of the cosine of H as it approaches 0, that approaches 1. And if we take the limit of the function 1 as H approaches 0, that's 1. And the sine of H over H is strictly greater than cosine of H at that point, and is strictly less than 1 at that point, and that fits our criteria for the squeeze theorem, meaning we have found a function we can take the limit of and a function we can take the limit of that we can sandwich this function nicely between, and so therefore at that point this is equal to 1 by the squeeze theorem. The reason that's an advantage is because now if you go back a moment and look, that tells us that we have the sine of x times 0 plus the cosine of x times 1 as our derivative, meaning the derivative of the sine of x is equal to the cosine of x. We're going to go ahead and prove the cosine of x next, but thankfully, because we've done this kind of stuff, it'll be a lot easier. Because we already did sine, look at how easy cosine is. We start with our definition. We work through it using our cosine angle sum theorem, which, is a little bit different. It's cosine of the first times cosine of the second minus sine of the first times sine of the second minus, of course, cosine, because we had it over here. We still collect up our like terms, but this time, when we do our factoring and distributing, we get cosine of x times the limit of cosine h minus 1 over h minus the limit of the sine x times the limit of sine h over h. And, well, we know that that's going to be the cosine of x. And we already figured out that this one was going to be 0 times 1, which is 0. And, well, that's going to be the sine of x. And we already figured out this one is 1. So, therefore, this becomes the cosine of x times 0, which is, 0, minus the sine of x times 1, which is, the negative sine of x. So, therefore, the derivative of the cosine of x is the negative sine of x. And now the nice thing is, because we found the sine of x derivative and the cosine of x derivative, when we do the tangent, we won't even have to go through this process. We can go ahead and use our quotient rule because we can redefine tangent. So just like I said, when we go to find the derivative of the tangent of x, we can simply redefine the tangent of x as the sine of x over the cosine of x, and then utilize our quotient rule. So before I do it, I'll give you a little bit of time to look at it and try it, and it's going to appear in 3, 2, 1. And there you go. So those are the 5 transcendental functions that most students are expected to know in an introductory calculus course. I hope the proofs for sine weren't too bad. If you do have any questions, feel free to drop into the comments or join us on Discord. In the next couple of videos, we're going to look at the last few rules that we're going to need to know so that we can start applying calculus to actual situations. I'll see you then.